Okay, 12.2.8 is describing the operations of an ideal transformer. So the student should be familiar with the working of a transformer from IGCSE, but basically a transformer consists of a soft iron core, okay, and there is an alternating current input and an alternating output, AC input here and an AC output over here. Okay, so what happens is basically when there is an AC input, there will be a current flowing through this coil which is wrapped around the soft iron core. Okay, now when there is a current flowing, there will be a magnetic field generated around the current, and that magnetic field, okay, the strength of the magnetic field is related to the number of coils on this turn, the number of turns on this coil. And let's say the primary voltage here is Vp, secondary voltage here is Vs, and the number of turns on the secondary coil is Ns. Now, the higher the number of turns on the primary coil, the greater the strength of the magnetic field generated. Now, since this magnetic field will be linked to the secondary coil over here, and because it's an alternating current, the magnetic field is changing. The changing magnetic field, okay, like we know, EMF induced is minus d phi by dt, okay, and phi is the flux consisting of Ba cosine theta, right? So the magnetic field now is changing its intensity with time because it's an AC input, and because of that there will be a EMF induced in this coil. Now you know that the EMF induced is equal to n times minus n times the rate of change of flux, okay? So over here n is the number of coils in the secondary coil. So the greater the number of coils in the secondary coil, the greater the output voltage, okay? So from this we have the primary voltage divided by the secondary voltage will be proportional to the ratio of the primary number of coils and the secondary number of coils, okay? And notice that we are talking about an ideal transformer. In an ideal transformer, it is assumed that there is no power loss in the iron core, but in real transformers you have power loss as heat in the iron core, okay? So this iron core is made of soft iron, okay? We also know that the power dissipation, since there is no power loss, the power dissipated in the primary coil is equal to the in the primary circuit is equal to the power dissipated in the secondary circuit. So Vp over Vs equals Is over Ip, and from here we have that they are equal to Np over Ns. Okay? Now, that's the functioning of an ideal transformer. Now, 12.2.9 is simply solving problems using these concepts. 12.3 is the description of transmission of electrical power. So now this is a very descriptive section. Some of it is also covered by the students in IGCSE, but basically this talks about how transmission lines work in accordance with transformers, and how transformers are used to step up or step down voltage. Okay, so when the number of coils here are larger, the voltage here will be larger than the primary voltage, and this would be called a step up transformer, whereas a step down transformer would be the opposite. Okay, so basically what it says is that in order to minimize heat loss in transmission of power, you need to use step up transformers so as to minimize the power loss in the transmission. So you can read and go through the students in this section over here, 12.3.1, why it is desirable to step up voltages to a high voltage in transmitting electricity over large distances, and then they step it down in order to provide a suitable voltage to wherever, like houses, industries, etc. So then there is a discussion of how power is lost in transformers due to the iron core, eddy currents in the iron core, a process called hysteresis, which includes heating up of the iron core, then copper loss, which is heat energy again lost in the in copper. So, and what are the ways? For example, laminations, which can be used to minimize this loss in the core of a transformer. 12.3.2 is explaining the use of high voltage step up and step down transformers in the transmission of electrical power. So this is what we were just discussing. There's a description here which can be discussed with the students. And following that is 12.3.3, solving problems on the operation of real transformers and power transmission. So basically you will have discussions of how the power loss is affected with real transformers, and how stepping up and stepping down transformers can be used in numericals. So again, a lot of descriptive stuff, so you want to probably go through this before the class as well, so that you can just describe the main significant features to the students. 12.3.4 suggests how extra low frequency EM fields, such as those created by electrical appliances, induce currents within a human body. Again, it's described very well over here, which also covers like why it is harmful for the human body. You can also have it combined with 12.3.5, where they're discussing the possible risks of working near high voltage lines. So basically suggesting that low frequency fields, extra low frequency fields are harmful for your health, and therefore pose like some work related health risks. So yeah, the last portion, 12.3, is very descriptive. You want to probably just skim through this for some sections of the exam or the exam questions which the student need to have a descriptive answer. So yeah, that pretty much covers electromagnetic induction. We'll move on to the next chapter from here.